Hello everyone, my name is Eldrick. Uh, right now I am in a vacation in Switzerland, and in this second I have some free time that I'm not sure of what I will spend it for. And I thought about making a YouTube video because I often make posts on Instagram in my account L Robotics about schematics, about problems, and yeah, I haven't posted in my YouTube channel in a while. So a random topic that came to my mind was the semiconductors behind a simple LED, those simple colored LEDs with two pins. And I would like to share about what I had learned about them. And I must say that I could be wrong in some aspects. And if that's the case and you recognize my mistakes, I hope you can correct me in the comments. And I'd be glad to be corrected. And I just want to share about what I had learned. So an LED is short for light emitting diode, and it has three main components. The first one is the bulb, the one that is colored. The second one is an anode, and the third one is a cathode. The anode one is the positive terminal, and the cathode is the negative terminal. And there's actually a fourth part in an LED. It is called the semiconductor material. It is inside the bulb itself. If you look closely, there's like a weird triangular thing inside the bulb, and that's the semiconductor material. So again, semiconductor is an object that can be both an insulator and also a conductor, which means that it can prevent electricity from flowing through it, and it can also let electricity flow through it. Uh, a slightly more technical definition would be that a semiconductor is an insulator that will become a conductor once it is exposed to certain factors. For example, light, heat, and also voltage. There's also some other uncommon sources of factors, for example, like sound. Usually, those kind of other factors they would be converted into voltage first, and then it will affect the semiconductor. So, for example, like sound, it's actually not the sound changing the semiconductor from an insulator to a conductor. It's actually sound being converted by a piezoelectric sensor into voltage. Then that voltage will change the insulator into a conductor. And an LED is a diode. A diode means that it is the semiconductor that changes its property into being more conductive once it is exposed to voltage, which means that it will become more conductive when it is charged. And another thing about an LED or a diode is that it only lets electric current to flow in one way. Uh, there can be several questions that can be derived from these two statements. The first one is, what even is the specific material, the specific thing inside the LED that becomes more conductive and was insulative before? And that material is actually the weird triangular thing that you see inside the bulb. There are two, and they are called the N-type and the P-type. The N-type is connected with the cathode, while the P-type is connected with the anode. And specifically what they are, the N-type is a combination of gallium and arsenide, gallium and arsenic, which is called gallium arsenide, with silicon, while the P-type is a combination of gallium and arsenic, which is gallium arsenide, and zinc. They use silicon specifically because when gallium arsenide is doped with silicon, it uh, will have 9 valence electrons, and the neutral atom have 8 valence electrons. So basically it has one too many electrons, and when it have one too many electrons, it will become negatively charged. That's why it is connected with a cathode, and that's why a cathode is called the negative terminal, because it is negatively charged because it has one too many electrons. And the same logic applies to the p-type. It is gallium arsenide doped with zinc. The result is an atom of 7 valence electrons, which is one too little valence electrons to become balanced, because you need 8. And that's why it's connected to the anode, which is called the positive terminal. And another question that could be derived from those two statements would be, how do n-type and p-type actually work? So first of all, n-type and p-type are located very closely. They are usually like 1 micrometer distance, uh, and in that 1 micrometer distance, they are merging. Basically, the n-type has one too many electrons, and the p-type has one not enough electrons. They could be referred to as one hole. They try to merge. And in this range where they try to merge, in this 1 micrometer range, it is called the depletion range. And the range from which part of the n-type shares its electrons and part of the p-type receives them, shares its holes, is called the p-n junction. And when an atom loses one of its electrons from the n-type to the p-type, uh, it becomes an ion. Basically, an ion is uh, a leftover atom after one of its electron had been shared or after it had gained an electron. So when the n-type shares one of its electrons to the p-type, it becomes a positive ion because it had lost one of its electrons. And when the p-type lost one of its holes, it becomes a negative ions because again it becomes a negatively charged because it lost one of its holes. And also uh, electrons and holes can recombine easily because they are free charge particles. And as a side note, I also bring a paper where I wrote my things, so this way I won't have to memorize this painful process for this video. Basically, an electron can combine easily with the holes because they are free charge particles, because they have higher temperature compared to the rest of the nucleus. And because of that, there's this thing called the thermal motion, which means that the ones with a higher temperature can move freely. However, the ions, they are unable to move. The leftover atoms, the atoms that had lost the electron and the hole, they are unable to move because uh, because they are stuck in a crystal lattice, and the crystal lattice is called gallium arsenide phosphorus. And this gallium arsenide phosphorus exists everywhere inside the bulb of the LED. Basically, every part of the n-type and every part of the p-type are encased in this gallium arsenide phosphorus. And there's a reason why the p-type and the n-type are encased in the gallium arsenide phosphorus. So it's about electric field. Electric field is the attraction and repulsion of electric charges. It can be between atoms, it can be between ions, it can be between subatomic particles such as electrons, protons, and neutrons, and it can also be from charged objects. And similar to magnets, the positive charge is attracted to the negative charge, like how the northern pole of the magnet is attracted to the southern pole of the magnet. And same, the negative charge is also attracted to the positive charge. The positive charge is also repelling avoid itself from another positive charge, and same with the negative charge avoids itself from other negative charges. However, despite those similarities with a magnetic field, it still has some major differences in the fact that once an electric field has been neutralized, for example, one positive and one negative, they have combined, they will no longer have any electric field whatsoever. Whereas magnetic field, once the south pole and the north pole recombine, they can still attract and interact with other magnets. They can still repel. They can still merge themselves with other magnets, not with electrical charges. This is why uh, both the ions in the p-type and in the n-type need to be encased in the gallium arsenide phosphorus, because we need their electric field. We need their electric field for uh, two purposes. So The first purpose is to let electric current from a battery pass through the LED. So usually the negative part of a battery is the negative terminal of a battery is connected to the negative cathode, whereas the positive terminal of a battery is connected to the anode. So in this scenario, which is called the forward bias, electrons will be released from the negative terminal of the battery and it will go to the cathode, and then it will interact with the n-type. And in the n-type, as I've mentioned before, they will have positive ions. Therefore, the negative electrons from this negative terminal will merge with the positive ions inside the n-type. And the result is that the electric field will become weaker because some of the positive ions are no longer pairing with the negative ions in the p-type. They have already paired with the electrons from the battery, and they will no longer need to pair with the negative ions in the p-type. Therefore, both the p-type and the n-type will lose some of its ions, and due to less ions, the electric field will become weaker. And due to weaker electric field, the electron can move through the LED much easily. And when the electrons from the negative terminal of the battery move through the n-type, it will get a small boost because the positive ions are attracted to the electrons. However, when it gets to the p-type, there will be negative ions, and because of that, they may get repelled from these negative ions in the p-type due to the p-type losing their holes, and because their holes are merging with the electrons from the n-type, they leave behind ions of negative ions. And yeah, the electrons from the negative terminal of the battery will be denied by these negative ions, and the result is a very small resistance, and usually this resistance is very small that it is not noticeable and it will just be ignored probably. And another fun fact is that when the current is higher, when the current is bigger, it means that there are more electrons flowing in a second, and because there are more electrons, they will bond with more positive ions inside the n-type, and because they bond with more positive ions in the n-type, there will be less negative ions in the p-type, and because of that, there will just be lesser resistance. This resistance part is not that important, and it's just like something that I thought was interesting. And okay, the second function of the electric field is that it can prevent current from flowing from the opposite side. So when electrons from the battery are exposed to the negative ions in the p-type, so again, in this scenario, the negative terminal of the battery is connected with the anode, and the positive terminal of the battery is connected with the cathode. This means that the electrons are released from the negative terminal of the battery to the positive to the p-type, which has negative ions, and the negative ions will repel these electrons. That's the first of all. And second of all, from what I've read, there had always been positive ions in the n-type and also in the negative ions in the p-type, and there had always been there due to the doping process with the silicon and with the zinc. But they are unable to create electrical field because the electrons in the n-type and holes in the p-type already bond with them. And in this scenario where the current is reversed, it's called reverse bias. When the electron is going to the anode and it exists through the cathode, in this case, the negative terminal of the battery attracts the holes of the p-type, and the holes of the p-type will leave those pre-made negative ions. So those negative ions that were made during the process of doping the gallium arsenide with the zinc, they will be left by the uh, holes, because those holes will be attracted to the negative terminal of the battery. The same goes with the opposite one. The positive terminal of the battery will attract the electrons, and because of that the electrons will leave their positive ions. Because of that, there are more positive ions and negative ions unsheathed. There are more positive ions in the N type and negative ions in the P type that aren't bound to the electrons and the holes that they are supposed to have. And because of that, they will form electric field. And this electric field will actually strengthen the original electrical field they were supposed to have in the depletion range. In other words, when you combine negative terminal of the battery with the positive cathode, positive anode, and the negative cathode connected with the positive terminal of the battery, the result is that the electrical field will actually get stronger. The result is that it will be harder for the current to move through the circuit, and that's why you cannot power on an LED. And that's also why an LED doesn't explode or doesn't break or doesn't burn when you apply the battery in the opposite manner, like I've just said before, like the reverse bias. That's why they don't explode. It's always interesting to me because when I do experiments with Arduino, I always expect one of my things to explode, because sometimes I put them in reverse. Turns out they don't explode, they just don't work because their electrical field is strong enough to prevent any current from flowing normally. I thought that's a very interesting thing. And given enough voltage, current may forcibly be able to turn on an LED. Basically, you can forcibly turn on the LED from the current going from the uh, anode, basically the negative terminal of battery, to the anode and exits at the cathode. However, it will most likely burn the LED and permanently damage it first before it is able to do so. Same with my point before, that you can probably almost set the resistance from the forward bias to zero with enough current, but that's probably not a brilliant idea. And it is about the main purposes of why the electric field are needed. And also, from these statements that I read, another question came to my mind. Why aren't these effects permanent? Why, when we unplug the battery, they still function? They can still function. They don't have that remaining electrons, and they can uh, be considered normal, and they're in the state before they were being charged, and they can be charged again, can be uncharged again, they can be plugged away, and nothing is left permanent to the circuit. And from my understanding, when the forward bias stops, electrons from the battery will leave the N type and stop merging with the positive ions in the N type, and the ions will eventually let go of its bond with the electrons from the negative terminal of battery, because usually a bond between electron and the ions only lasts a few nanoseconds or microseconds, but it happens again and again constantly, to the point where it seems like they just keep on bonding. However, this bond actually breaks away every short microseconds, and when you unplug it, it just stops. It just stop bonding, like it always do. Except this one, it doesn't rebond again because there's no electrons to do that. Then again, thermal motion will happen, which is like, as I've said before, the electrons and the holes just wandering around, and this happens so fast that they will bond with each other again. And when they bond with each other again, they will create the positive and the negative ions again, which cannot move because they are in a crystal lattice of gallium arsenide phosphate, and because of that they will create the electric field again, and thus the electric field will be restored, because even if it was weakened, those free roaming particles will eventually cause the creation of the ions, and those creation of ions will create that electric field again. And in the reverse bias, it's a bit different. The battery will stop pulling electrons in the n-type to the positive terminal, and will stop pulling the holes in the p-type to the negative terminal. And again, with the thermal motion, electrons and holes will move randomly, and they will at some point move back to the p-n junction, and they will neutralize the original ions from the doping material. So like as I said before, the doping materials left behind ions, and when these ions are immediately bounded by the electrons and the holes, these electrons and holes are being attracted to the terminals of the battery, which causes them uh, to leave the ions open, and these ions open will create stronger electrical field. But once there is no more battery, they will roam again, and they will bond again with the ions, and soon enough the electric field will be restored back to its previous state. It will not be as strong again, and the depletion region will also be at its previous state. So in summary, the restoration of both forward bias and reverse bias happen in milliseconds, microseconds. And maybe the last question that we can ask is about the color of the LED. Like, how are they able to make the color red, yellow, and green and blue in LED? So it's actually an interesting topic, because I thought there will be more parts of this from an electrical point of view, but turns out it's just because of the material. And maybe I should dive deeper into why these certain materials causes the creation of this light, but I haven't. And in summary, gallium arsenide phosphate will create the color red, yellow, and green. You just have to slightly adjust the amount of gallium, the amount of arsenic, and the amount of phosphate in order to make the LED more red, more yellow, or more green, or even more turquoise. No, not turquoise, like I forgot the term for the color, lime, more lime, which is between yellow and green, or more orange. So in summary, to create the color red, you need about a scale of 1 for gallium, 0.7 for arsenic, and 0.3 for phosphorus. And to create the color yellow, you need approximately 1 for the gallium, 0.5 for the arsenic, and 0.5 for the phosphorus. And to create the color green, you approximately need 1 for the gallium, 0.3 for the arsenic, and 0.7 for the phosphorus. So essentially, those are the scales that you need for the amount of element to create this material for the LED to be red, red, yellow, or green. And again, this material is placed as the block, as the crystal lattice that makes the atoms and the ions in the n-type and the p-type holds their place. So again, this compound have two purposes. The first one is to make sure that the ions from the n-type and the p-type don't wander around freely. And the second one, because if they wander around freely, they will just merge with each other and just no longer have the electric field, so they need to be maintained and stuck to their place. And the second one is to create the color. And interestingly, to create the color blue, you cannot adjust any level of phosphorus. You need to actually use an entirely new compound, which is gallium nitride, in a scale of 1:1. So there's an equal amount of gallium and an equal amount of nitride. There is no arsenic involved. And the most interesting part about this is the fact that the color red, yellow and green was founded in around 1950s. They were able to find they were able to create the color LED for the red, yellow, and green in the 1950s to the 1960s. However, it took them another 30 to 40 years until 1993 or 1992 to create the color blue. Yes, and the reason is very simple. It's because you cannot create the color blue from adjusting the same material that they used for red, yellow, and green. They need to use an entirely new material, which is nitrate, and to remove the arsenic. And I think it's just a very interesting topic about sciences. Like, for example, you cannot yet easily just use sound to make an insulator more conductive. You need to make them into voltages first before they are able to be used for the semiconductor. And yeah, just like uh, there's always like secrets and maybe unknown passageways to get to the goal that we want in sciences. And I think that's what makes engineering and what makes research very fun. So again, I just want to share this from what I had learned. And actually, a big motivation of making this video is because I have read some studying tactics, and they involve like uh, sharing it with others, and this is why I'm making this video. I am very certain that this video is quite accurate. However, if there are inaccuracies, I hope you will mind to share them with me. Thank you so much for listening. If you did listen to this almost 30-minute video, and I hope I didn't waste too much of your time. I also would like to share about the view of Switzerland, maybe. There's nothing to view at from this perspective, basically, because I am in my apartment, and yeah, there's not a lot of views from my apartment directly. Okay, that's it for my video. Thank you very much.